In this video, we will give a systematic method for the analysis of electrical circuits called mesh analysis. Before we describe this method, we will give a few definitions that will be used. The first definition is of a planar circuit. A planar circuit is a circuit that can be drawn on a two-dimensional surface, for example paper, without any wires or elements crossing each other. We will underline a few words in this definition to stress upon some key ideas. A planar circuit is a circuit that can be drawn on a two-dimensional surface, for example a paper, without any wires or elements crossing each other. Consider the circuit shown on screen. It has a voltage source and resistors in it. There are two resistors, R1 and R2, which seem to be crossing each other. We will redraw the circuit and begin with all the elements that do not cross each other. We will draw the resistor R1 next from node B to D. Resistor R2 is connected between nodes E and C, and we can draw it in a different manner such that it does not cross any other element or wire and is still connected to node C as shown on screen. Since we have been able to redraw the circuit without any wires or elements crossing each other, this circuit is planar. The next circuit that we will look at is given on screen. In this circuit we have two resistors, R1 and R2, which are crossing each other, and we cannot redraw this circuit so that these two resistors do not cross each other. Therefore, the circuit is not planar. The reason for distinguishing between planar and non-planar circuits is that mesh analysis applies only to planar circuits. Continuing with definitions for mesh analysis, we will define a mesh next. A mesh is a loop that does not enclose any elements inside it. For example, in the circuit shown below, we have four meshes: A, B, C, A, B, C, D, B, C, D, E, C, and A, C, E, A. None of these loops enclose any elements inside them and are defined to be meshes. An easy way to identify meshes in a circuit is to identify small windows in the circuit. For example, this is the loop ABCA, and the other loops that we have defined are small windows in this circuit, and none of these meshes have any elements enclosed inside them. We define a mesh current next. A mesh current is a circulating current that flows only in the mesh defined by it. The direction of the mesh currents is arbitrary. However, we will take all the currents to be flowing in the clockwise direction. For example, in the circuit shown above, all the currents I1, I2, I3 and I4 are flowing in the clockwise direction, and they are called the mesh currents for the meshes defined by them. Note that each element in the circuit will be parts of one or two meshes. For example, the resistor R1 is part of the mesh defined by the current I2, and the resistor R2 is part of two meshes defined by the currents I2 and I3. Since R1 is part of the mesh defined by the mesh current I2, if you are interested in the current flowing through this resistor in the direction shown, then the current I will be equal to the mesh current I2, since both I and I2 are flowing in the same direction. The resistor R2 is part of two meshes, one defined by the current I2 and the other defined by the current I3. If you are interested in calculating the current through the resistor IR2 in the direction shown, since the mesh current I2 flows in the same direction as IR2, it will show up with a positive sign, and the mesh current I3 flows opposite in direction to IR2, and it will show up with a negative sign. And the current through the resistor IR2 will be equal to I2 minus I3. Finally, we will give a definition for mesh analysis. For mesh analysis, we will write KVL equations for all the meshes using only the mesh currents as the unknown variables and using any known element values. We will apply mesh analysis to the circuit shown. We note that it is planar and there are two meshes in the circuit which are defined by the mesh currents I1 and I2. We will write KVL for the mesh defined by the current I1, and we will start from node D and go to node A. We have a voltage rise of 2 volts. Voltage rises are given a negative sign, so we'll write down minus 2 volts. For the 2 ohm resistor, the mesh current I1 is flowing from node A to B, which will give us a voltage drop with the polarity shown. Following the convention of giving voltage drops a positive sign, we will write down that the voltage will be 2I1. For the 4 ohm resistor, the current flowing in the downward direction, we will call that I4, and I4 will be equal to I1 minus I2. And the voltage drop across this 4 ohm resistor, given with a positive sign, will be 4I4 or 4 into I1 minus I2. And this will be equal to 0 to satisfy KVL. Next, we will write KVL for the mesh current I2. The voltage drop across the 4 ohm resistor in the direction of the mesh current I2 will be 4 times I2 minus I1. The voltage drop across the 1 ohm resistor will be 1 times I2. And finally, we have another voltage drop of 4 volts, which will be written as plus 4, and this is equal to 0 to satisfy KVL. We have two equations in two unknowns, and we can solve these for the mesh currents I1 and I2. And the solution will give that I1 is equal to minus 3 over 7 amperes and I2 is equal to minus 8 over 7 amperes. The negative value for both mesh currents tells us that the mesh currents are actually flowing in the opposite direction, that is anti-clockwise. Once we have solved for the mesh currents, we can calculate any other voltage or current in the circuit. For example, if you are interested in the voltage across the 4 ohm resistor, assuming that the current through the resistor is given by the direction of I4, then the polarity of this voltage will be as shown. And V4 will be equal to 4 times I4 will be equal to 4 times I1 minus I2, which will be minus 3 over 7 minus 8 over 7, and is equal to 20 over 7 volts. To summarize mesh analysis, we first identify that the circuit is planar. Next, we identify the meshes in the circuit. Next, we write KVL equations for all the meshes in terms of the mesh currents and other known element values. We solve the KVL equations written for the mesh currents. And finally, we can solve for any other voltage or current in the circuit using the known values of the mesh current.